In this video, I will give you an explanation of the basics of X-ray Photon Correlation Spectroscopy, or XPCS for short, and how we can use this technique to get information about the structural kinematics and dynamics of molecular systems on time and length scales that are typically on an atomic scale. Time scales from hours to picoseconds are accessible. For example, slow processes like protein aggregation typically occur in the range of minutes to hours, conformational transitions in seconds to microseconds, and molecular tumbling in the time frame of multiple nanoseconds. In addition, length scales from micrometer down to nanometer can be measured. This information is provided by analyzing the fluctuations of the nanostructures present in your sample. All living beings are made of trillions of living cells, which all perform many different tasks. So let's have a closer look at the dog over there. We can see that its cells consist of a variety of different macromolecules such as amino acids, proteins, sugars and salts in a very narrow space surrounded by water. Diffusion within the cell can strongly influence the reactions between these macromolecules and thus the functionality of the cell itself. Understanding the dynamics of these crowded environments is therefore of utmost importance. So, let's have a look at the diffusive behavior of the macromolecules. Imagine a protein molecule surrounded by water. From time to time, the water molecules collide with the protein, resulting in random fluctuations of the protein. This type of motion is called Brownian motion and depends on the size of the protein. Smaller proteins diffuse faster, while larger proteins diffuse much slower. This behavior can be described by the Stokes-Einstein relationship, in which the diffusion coefficient d is related to the sample viscosity eta and the particle radius r. So, how do we use XPCS to measure the diffusive motion of our sample? For an XPCS experiment, we need a highly intense, coherent X-ray beam, which is provided by a storage ring. The beam size is then reduced to the desired shape and required energy by the beamline optics, such as mirrors, collimators and monochromators. Now imagine the X-ray beam falling onto the static protein molecules in your sample. Differences in the electron density lead to small parts of your beam being scattered. Constructive interferences of those scattered X-rays result in random bright and dark spots on the detector, the so-called speckle pattern. To measure these fluctuations, a detector with a high frame rate is required. To protect the detector from the unscattered beam, a beam stop is positioned in front of the detector. By analyzing the temporal correlation of the speckle intensity, you can deduce the dynamics of your sample. Before we go on to explain how correlation works, let's summarize what we've learned so far. When we perform an XPCS experiment, we take several snapshots of the scattered intensity in quick succession. These snapshots will then be correlated to the original signal measured. If the delay time between two snapshots is short, the particles didn't have the opportunity to move far away from their original position, and the similarity or correlation between the two intensity signals is high. However, if the time between the snapshots is increased, the similarity or correlation decreases exponentially, and after some time there is no correlation at all between the two signals. This is called temporal autocorrelation and can be represented by the so-called second-order correlation function, or G2 function for short. If the particles in your sample are moving at a faster rate, the signal will be lost after a shorter amount of time, while the decay of your autocorrelation will take more time if the particles are moving slower. We can now use this autocorrelation function to get some information about the dynamics in our sample. For example, we can fit a function of the form shown here to the measured signal. Here gamma of q represents the q-dependent relaxation rate and alpha of q the Kohlrausch-William-Watts coefficient, or kWw for short. The latter is closely related to the type of dynamics present in the sample. In the case of Brownian motion, we obtain a kWw value around 1, while faster processes, such as superdiffusive motion, result in a value greater than 1. Slower processes like glassy transitions lead to a kWw value smaller than 1. Now that we know how to get information about the dynamics in our sample using XPCS, you might ask yourself what real-life problems and applications we can tackle with this technique. We already established in the beginning that the diffusive behavior of proteins in a crowded environment, such as the living cell, can have a strong impact on its cellular mechanisms and functionality. This knowledge is not only important for modeling these mechanisms on a nanoscale, but also for the pharmaceutical industry to develop future protein drugs for treatment of many diseases like multiple sclerosis, Alzheimer, and cancer. A major challenge in drug formulation is the aggregation of highly concentrated monoclonal antibody solutions, which might lead to harmful immune responses. To fully understand the mechanisms of antibody aggregation and achieve long-term stability of the antibody solutions, knowledge of the underlying kinetics and thermodynamics is of utmost importance.